Hello and welcome back to Calculus 1 section 4.5 on optimization problems. These are the word problems where we find min and the max, the points at which min and max occur. We are interested in maximum profit, minimum cost, maximum maximum volume, minimum surface area, minimum distance to get places. So we would like to find the way to compute these things rather than use the guess and check method, which can be really annoying. Now let's take a look at the guess check method first and then see the proper way to solve it using calculus. Say sum of two numbers is to be 12. Find x and y such that their product is maximum. So what do we do? Well, 0 plus 12 is 12. And when you multiply, you get 0. So, meh. But then 1 plus 11 is also 12. And when you multiply, you get 11. Well, that's much better. Then 2 plus 10 is also 12, and 2 times 10 is 20. Well, that's even better than 11, right? We are looking for product to be as big as possible while maintaining the sum of two numbers to be 12. So 3 plus 9 is also 12. 3 times 9 is 27. Well, that's better than 20. 4 plus 9 is, 4 plus 8 is 12. And what's 4 times 8? It's 32. And that's even better. 5 plus 7 is also 12. What's 5 times 7? Is 35. 6 plus 6 is also 12. 6 times 6 is 36. That's even better. Now we have 7 plus 5, also 12, and now we see that it starts going down. It's 35. So by guess and check, we found that if we use x equals y equals 6, we would have a maximum product, right? Because as I keep going over here, it's going to start decreasing again until I reach 12 plus 0 is 12, and then product is 0 again. So we were able to discover using guess and check method. Now obviously when the numbers are much larger, good luck with that, right? So is there a way to solve this using calculus so we don't have to do all of these annoying things? What happens if I say that the sum of two numbers is 72, right? Go ahead, figure it out. So we are going to transfer that word problem into mathematical expressions which are known as equations. So we have x plus y needs to be 12. So something like this will be called constraint. So constraint equation. And then x times y needs to be max. Well, this is our objective because we are trying to find the maximum value, right? So we have objective equation and we have a constraint. So now we need to solve this. Now you technically have three unknown variables, right? X, y, and max. Because you don't know what that max is. Well, you do know it's 36, but because you actually solved the problem by guessing and checking, right? But you need to know that x is 6, y is 6, and max works out to be 36. Now, the issue is that you have two equations and three unknowns. right? So we have to use some clever method to solve this. So this is what we do. You take constraint equation and you solve it for one of the variables. So y is equal to 12 minus x, and you plug in into the objective equation. So now it's x, 12 minus x equals to a max. That's 12x minus x squared equals to a max. Now, let me write that in blood actually. Max slash min is a constant number. So that's very important, right? It's a number. So now, when I differentiate in respect to x, we are actually looking for maximum. That's how we're going to find the x value at which maximum occurs. Now, what happens when I differentiate this? Max becomes 0 because of that. Now, we also know that you find min and max when you set the equation equal to 0, but over here we don't have to set it to 0 because it's already equal to 0. So all of those pieces from before, from 4.1, now fall into place. So we read the word problem, we come up with two equations, then we solve for one variable, plug in objective equation, and then differentiate to find, as you can see, that x is equal to 6. Then we have that the y is equal to 12 minus x, which is 12 minus 6, which is again 6. And now we have that y is 6. So we find that is x is equal to y equals to 6. We have max product. We determined that earlier, right? We determined that one earlier by simply guessing and checking. But again, when you have small numbers, it's not a big deal. But if you have large numbers, it is a big deal. If you think of, let's say, you want to maximize the volume of this classroom, therefore, right, to put, but you want to keep the height to always be 10 feet because that's the standard to the ceiling. Well, the ceiling is a little bit lower because it's dropped ceiling, but from the floor to the top is 10 feet, right? This is about, well, maybe it is. I don't know. Maybe 9. So you want to calculate min and a max given situation. And that's what we have. Let's see. Some of the famous problems are farmer's problem. So farmer wants to fence off a rectangular plot of land so that it has maximum area. Let's say you want to keep some kind of animal there on a pasture. So the larger the area, the more grass, right? Or the larger the area, the more trees you can plant. Orchard, right? Apples. Now, what is the issue? The issue is that farmer will have a set amount of fence, 2,000 yard of fence, 1,000 yard of fence, whatever, right? So farmer is going to have some amount of fence, which is your constraint. You don't have anything anymore, right? That's all you have. So that's a constraint. And then, what is the maximum area that I can fence off with that much fence? So Farmer has 2,000 yard of fence. He wants to fence off a rectangular plot of land. So he wants to fence off a rectangular plot of land of max area. Find the dimensions. Well, luckily, our farmer knows calculus. What do? We draw rectangle. That's x, that's y. And then we translate our word problem into mathematical equations. So what's the first sentence? What mathematical equation do I get to write? 2x plus 2y equals 2,000. Excellent. Because the fence goes on the perimeter of the rectangle, also known as a perimeter fence, right? So to go all around where the black line is, right, it's 2x and 2y's. Then, what's the second equation? Well, he wants maximum area. What's area of the rectangle? xy, and that needs to be max. When you divide by 2, you get x plus y equals 1,000, and then xy equals a max. This worked out to be the same problem as the previous one, right? Except in the previous one we had 12 over here. It's the same thing, right? So, y is equal to 1,000 minus x. Plug in, this is absolutely the same. We have x times 1,000 minus x equals a max. 1,000x minus x squared equals a max. Once it has one variable, hit that with the derivative. And then we have 1,000 minus 2x equals 0. Derivative of max is 0, because max is going to be some area. I don't know, 25,000 square yard. 25,000 is a number. When you take the derivative of it, you get 0. So now from here, 2x equals 1,000, x equals 500 yard. And then we use the y equal 1,000 minus x, which is also 500 yard. And we found that if he fences off a square, 500 by 500, he will have max area of 25,1212. So 250,000 yards squared. Now we get to modify this. Previous problem was 6 and 6 to give us 36. Now it's 500 and 500, right? Is it always a square? No. Depends on geometry of the problem. So now, if I have a river, and we know it's a river because there's salmon in it, now a student said those look like carrots, but they're not carrots because the carrot would look like this. with the green over here, right? That's a carrot. This clearly has, right, an orange tail as well, so it's a salmon. Now, we put our XY plot of land where the black line represents the perimeter fence. So now what I have? I still have 2,000 yard of fence. So what's now?
2y plus x.
Yes. So x plus 2y is equal to 2,000, and we still have xy equals a max because we are looking for the maximum. So this changes calculations, right? Now you want to solve for x on top to avoid fractions. So 2,000 minus 2y. Then you plug this instead of x. You get 2,000 minus 2y times y equals a max. So now you will solve for y first. It's a 2,000y minus 2y squared equals a max. And then you differentiate now in respect to y. So that's going to be 2,000 minus 4y equals a 0. And y is 500 again. But x is not going to be 500. Because x is 2,000 minus 2 times 500, 1,000 yard. So now, for max area, when you have this configuration, is 1,000 for x by 500 for y yard. That will give us max area equal to 5, 1, 2, 3, 1, 2. 500,000. Clearly it's bigger, and it's bigger because we do not have to fence off one of the sides. So the entire one side, because we are using river as a natural fence, right? Animals don't know to swim, right? Unless the grass is greener on the other side. So. Now, how about if farmer has things that he has to separate? So he has to create bins. Like cabbage, rabbits, and tigers. Right? Can't put them together. Can you imagine a rabbit and a tiger in the same one? No. Right? It would just be tigers. One of the funniest comedy sketches I ever heard on the Noah's Ark nonsense story is like the all right, we get 2 of each animals. So you have 2 lions go on board, then you have 2 tigers go on board, then you have the 2 zebras and 2 antelopes and 2 sheep and 2, right? And then after, you wait for a lot of animals to pass, then you take a look at the ark. What's on the ark? Well, 2 lions and 2 tigers. That's it. Like nothing else. So the rest is shredded, right? So now we want to make sure we separate tigers from rabbits. So we need these different bins. So we have all these y's over here. We have the x's on top and the bottom. And this changes our story more. So now you have 2x plus 2y plus 4y equals 2,000, and you still have xy equal max, because you still have length times the width, which is a y, and calculation is always the same. Guys, any problem that we do, even when we move away from the farmer in the next problem, you're still going to have the same. You solve one equation, well, you divide by 2 first. So x plus 2y is equal to 1,000 now. And you solve for x, 1,000 minus 2y, and then you plug in. So all of these problems are going to be exactly the same for you to solve. You will take the constraint, solve for one of the variables in a constraint, and plug that into objective equation, and then hit that with the derivative. So instead of x, we have 1,000 minus 2y, everything times y equals to a max, which is 1,000y minus 2y squared equals to a max. And now you hit this with the ddy derivative, which is 1,000 minus 4y equal to 0. So y equals 250 yard. Now clearly this has to be the smallest of all because we use a lot of fence for the inside fence, right? For these two over here, we are using fence to put that up, so that impacts the amount of fence that I have left to go around. So since I have less fence to go around, the overall area must be smaller than in previous cases. So now I have that the x is equal to 1,000 minus 2 times 250, which is 500. So this one would be 500 by 250 yard to get the max area of 5 times 25 is 125, and then 3 zeros. So it's a quarter of the previous area. So all of these optimization problems that we have done so far and that we will do in the future, all of these problems have the same idea. You write two equations by reading the text. One of them will be constraint, the other one will be objective. Then you plug constraint into objective to eliminate one of the variables, and then you differentiate, which will give you immediately the point of interest. So let's take a look at some of the problems in the book. So now that we covered this lecture, we have a problem that is going to be opposite of the problem that you have for your project, which I can finally give you because we are covering this, right? We're covering this particular formula, and that is going to be minimizing the surface area or maximizing the volume of a box. So packaging engineering is a booming field, and apparently you're getting jobs before you graduate. And in that engineering, you are concerned with creating boxes and also designing the stuff for to enclose the electronics, like plastic, but also boxes to ship stuff. And maximum volume does what? Allows you to put a lot of stuff inside, right? So max volume makes sense. Why would you want minimum surface area? What would that help with?
Save cost.
Save cost, very good. Because you can maybe minimize and save 2 or 5 cents, for a box.
Yeah, put that projector right there. Instead of making it square, it's weird shape.
But why would you want to save, 5 or 10 cents per box? I mean, what's the big deal? Ah, yes. When you have 10,000 boxes, right? Like, would you like 5 cents? You go, I'll pass. How about 5 cents times 50,000? Would you like that, right? So that's where the cost reduction is, because the company is not going to ship one box, right? They're going to ship maybe 50,000 boxes. 50,000 boxes times 50 cents, all right? That's $25,000 savings. So that's a big deal, right? So we do want to minimize surface area of boxes. We do want to maximize the volume so we can put as much stuff as possible. So here's a problem that says minimum surface area of the box. Your job for the project is going to be to make the largest possible volume. So minimum surface area of the box. Of all boxes with a square base, of all boxes with square base and a volume of 8 meters cubed, which one, in terms of dimensions, has a minimum surface area? So which one of these boxes has the minimum surface area? That's our question. Okay, well, we can deal with that. We start by understanding that we have a square base. Now, why do we need a square base? Well, because it's Calc 1, it's not Calc 3. You will do blocks of any kind in Calc 3, and you will use something that it's extension of this, which is called, what is it called? It's called Lagrange multipliers. Guys, you can only work with two variables and then eliminate one and then differentiate, right? So if I have a square base, then that's just going to be x times x. And then the height of the box is y, so I have x and y and we're good to go. If I allow for a non-square base, then I have x, y, and z, and you can't eliminate two variables. So that's the issue in Calc 1. So we are stuck. We are stuck with one box. I mean, square base on a box. Okay, so I have a square base for this box. X and x. Right? So that's the square base. And then I have a height of y. Could be higher, could be lower, I don't know. So what do? I need volume to be 8. What's the formula for volume? Well, that's base times the height, so x squared y. X times x is the area of the square, which is on the base. And then times y, which is the height. And that needs to be 8. Well, this is our constraint. Very good. Because it has all of the information given. Now, how about my surface area? Well, we are sitting in a box right now, right? You have a floor and a ceiling, and you have 4 walls around, 6 sides. So, surface area is 2 times x squared for a floor and a ceiling. And then plus 4 sides that are all the same, because you always have x on the bottom and y as a height. And that needs to be minimum. We all see that? So now, then that's our objective function. So now, we solve for y as 8 over x squared, and we plug in into objective function. So 2x squared plus 4x times 8 over x squared is equal to minimum 2x squared plus 32 over x equals a minimum. And now we hit this with the derivative. So this is 4x minus 32x squared equal a 0. So 4x is equal to 32x squared. 4x cubed equals to 32. X cubed equals to 8. X equal 2. You take cube root of both sides. Now, y is 8 over x squared, which is 8 over 4, which is another 2. So our box is 2 by 2 by 2 meters, which will give us the volume of 8. Well, 2 times 2 times 2 is 8. And the minimum surface area, which is going to be actually a square on each one of the 6 sides. This is why the cube is the special perfect shape, because it will give you maximum volume, it will give you minimum surface area, and all the sides are the same. It's an amazing shape, right? The only one that is better than that one is a sphere. Now, what do you have for the project? For the project, you are charged with the task to take, this is one of the problems, to take a single printing paper and first create the square, right, and throw the rest. And out of the square that is left, to create the largest possible box with no top, meaning maximum volume, right? So that's the job for the project. And you make it out of paper, you can decorate, right? And bring it for the final. So that's one of the 3 problems. It's hands-on, and it's calculation, and it's this section. So you would have to figure out the way to, we just missed the things about the project. You will have to figure out the way to compute things and then make it. Let's see what else. Closest point on the line, 22. What point on the line y equals 3x plus 4? This could be anything, could be sine, could be ln, could be any function out there. Is closest to the origin. It doesn't have to be origin, could be any other point, 1, 3. So the function can be any function out there, square root of x, ln x squared, whatever. And then the point of interest could be any other point. Now, being that this is introductory, right, we use the easiest possible situation of a linear line and the point at its origin. So to understand this, we draw 1, 2, 3, 4, 3 units down, 1 units over. So this is the linear line. And perpendicular to that, getting out of origin, which is 0, 0, and this is what we have. So we are looking for this unknown point xy that lives on the line which is closest to the origin. Well, constraint is already given to us. You can call it well, y equals 3x plus 4, right? That's a constraint right away. Because the point has to be on that line. That's the constraint, right? Now, what's the objective function? What am I trying? The word closest is related to what concept that we are working on right now? Closest is minimum, okay? So closest is minimum, great. So here I'll put min. Now, what am I minimizing? What am I minimizing? Read the problem. What am I minimizing, guys? Distance, exactly, thank you. This distance d is the distance between x, y, and 0, 0. And I just want to have that as small as possible because that's what the word closest means. So the distance formula, if you forgot, is the square root of x2 minus x1 squared plus y2 minus y1 squared. In my case, x1, y1 are both zeros, and this is x and this is y, because one point is xy, the terminal point is xy, and the origin point is 0, 0. So, I am minimizing the distance formula, which is x squared plus y squared equal min, and that's my objective formula. So, I need to be dramatic. We plug in, have a square root of x squared plus 3x plus 4 squared equals a minimum. Square root of x squared plus 9x squared plus 24x plus 16. When you square this, don't forget the middle term, 24x. Square root of 10x squared plus 24x plus 16 equals a min. There we go. Hit this with the derivative. And get 20x plus 24 divided by the square root of 10x squared plus 24x plus 16 equal to 0. And when you cross multiply, you get 20x plus 24 is equal to 0. X equals negative 24 over 20, cancel by 4, negative 6 fifths. It makes sense for it to be negative 6 fifths because look, that's where the negative numbers are. So negative 6 over 5 is the x coordinate. And now are we expecting a positive or negative y? Positive y, great. So y is 3 times, so y is 3 times negative 6 over 5 plus 4. This is negative 18 over 5 plus 20 over 5 for a total of 2 over 5. So x is negative 6 fifths and y is 2 fifths, and that point is closest point to the origin. Would something like this be somewhat relevant to GPS? Right? You want to find the closest way to get to your new friend's house, right? You've never been there, you use the GPS. 100,000 jobs available in computer science, which is programming GPS, for instance. Great. So I'm going to modify the problem that they have in the book. We'll do 2 more examples. All of the examples are the same. Equation number 1, equation number 2, plug one into another, differentiate, you're done. So all of the problems are the same. It's just what is the situation, do you see the geometry, and what do you get to take out. So for this problem, they have a flower garden, and then they have the grass around it. Now, I'm not going to use those because that's incredibly stupid. No one calculates this stuff. What people calculate is how much concrete they need to pour around the pool. So, instead of flower garden, I'm going to have a pool over here, which is 30 meters square. It's a pond. You build something for your local frog, because 30 meters squared is nothing, and you will see the dimensions of this are a joke. But it's a much better idea, right? And around the pool, right, you want to pour concrete so that when kids run and fall, they scrape their knees. Obviously. Right? So now, they say, what dimensions do we need to minimize the combined area? Your pool is 30 meters squared. That's fixed. So you can't get less of a pool. But minimizing the whole area is minimizing what? Is minimizing the amount of concrete that you are going to use to have exactly what you want. Because if you need 2 meters on one side, 2 meters on the other, that's my height, right? 2 meters. So it's one of me on one side and then half of me on the other sides. By minimizing the entire area, I get to use the least amount of concrete. Now, let's write some dimensions. The pool inside is going to be xy, because that's what they're looking for. They're looking for dimensions xy for the pool, and as soon as you have those, right, you know immediately what the outer ones are, but such a way that we get a minimum. Great. So now, if the inner sides of the pool are x and y, what are the outer sides? What is this? Let's see who knows to read technical drawings. Yes?
X plus 4.
X plus 4, excellent. Because the pool in the middle is x, and then you have 2 on each side. So 2 plus x plus 2 is x plus 4. And the height is what?
Y plus 2.
Y plus 2. Great. Because the height of the pool is is y, and then you have 1 over here and 1 over here. So 1 plus y plus 1 is total of y plus 2. Perfect. So now we have our constraint equation. What is the constraint?
xy
Equals 30. Yes. So xy equals 30. That's the area of the pool given in the middle. It could be a jacuzzi. All right. So This jacuzzi for a maximum occupants of 30 people if you just file them to sit, right? Next to each other. Because you occupy 1 meter squared of space, right? So 30 would be 30 people. But they're all densely packed, which is usually what actually happens anyway. So, we have this. Now they want to minimize the overall area. So what's my objective equation?
X plus 4 times y equals 2.
X plus 4 times y plus 2 needs to be minimum because we want to minimize. So as soon as you get this, go ahead, y equals 30 over x, plug it in the bottom, FOIL everything, hit it with the derivative. You got your x, and then you go compute the y. So y is equal to 30 over x, and you plug that in. So now we have x plus 4 times 30 over x plus 2. FOIL everything, that's 30 plus 2x plus 120 over x plus 8 equals a minimum. 2x plus 120 over x plus 38 equals a min. There it is, only one variable, x. So we can hit this with the derivative. 2 minus 120 over x squared equal to 0. Derivative of 38 is 0. Derivative of minimum is 0. So that all goes away. We have 2 equals 120 over x squared. Cross multiply. 2x squared equals 120. X squared equals to 60. If you find the square root of 60, $7.75. It should be positive or negative, but we don't use negative because these are distances, right? And they're never negative. And now to find my y is 30 over 7.5. So 30 divided by 7.5 is 4. Meters. So pool is 7.5 by 4 meters, and that will guarantee the smallest combined area. Now when you take away the 30 meters squared for the pool that is set in stone, the rest is going to be the concrete area, and it's because it's minimum, you get to use the least amount of concrete, you get to save on the cost. So this is, one of the problems. Now, sure, I mean, you might find a job to to do something like this, but remember how your textbooks are $1 million per page, per book, right? So there are companies that are making these books, right? They're printing the books, and they're using these calculations actually, because you have a page and then you have margins. Wouldn't this look like a page in a book with margins on the side? If you have a 1 inch, half inch, and half inch, or maybe 1 inch and stuff, right? What do you have? You have the set amount of inches squared for the text, and then the margin around. by minimizing the total area of the page, you're saving on cost, right? Because minimizing, if this is a page and you have the text inside, by minimizing combined area, you are minimizing the size of the page, which is paper, right? Times 100,000, 200,000 copies, right? And each one has 1,500 pages, like your calc textbook, right? Per page. If you save a third of a cent times 1,500 times 200,000 books.
Plus it's lighter, so you can stack more of them like stuff.
So it's a lot of savings, right? It's a lot of savings. So guys, when you are out in a field, these things are computed. These things are computed because they are saving money. And it's important for a company to save money on a cost, because anything that is not spent as a cost stays as a profit. And a profit is important for a company. Each company must have profit, because profit is the one that allows companies to hire engineers and research and development to make new stuff for the, right? The profit is not going somewhere, under the mattress. I mean, there is always corruption here and there.
Yeah.
Well, let's not, the trick is that if the company comes up and never makes anything other than the first version of cell phone, then, and other companies did, right? So that's where the profit goes. Because when you are creating something, you have to buy the materials, you have to make the thing, you have to ship the thing, you have to sell the thing, you have to buy and rent the place to like a showroom and all that stuff, which is why Amazon is killing. They don't have that, right? Like Best Buy has buildings all over Walmart has buildings all over the place. How many times did you go to any of these stores, look at the object, play with the object, say, oh, this is a really cool thing, I'm going to buy that, and then you go and you buy it on Amazon, right? Because it's cheaper. Amazon can charge less because they don't pay for employees and workers in a showroom, which is Walmart is a showroom and Best Buy is a showroom. All of these places are showrooms because they have, right? So these are the things that we have. The last problem that I want to work out is, again, another modification on what they have in the book. Just to show off the idea on, of, again, you being a consultant for one of the industries that are still extremely powerful and relevant in our day and age, and that is oil industry, right? So if you, let's make a scenario over here. So this is a shoreline. So shore and a sea, shore or land. And here be an oil rig, which is, let's say, 2 miles away. And then over here, I'm going to have a refinery, which turns oil into gasoline or plastic. I mean, all of those products, right? Rubber, all of those products are from there. Now, and let's say this is 5 miles here. So this is a short distance. You are not going to have a tanker going back and forth, because tanker can't even turn properly in 2 miles. So you put pipes, and you can just shoot the crude oil directly, right? Now, to install underwater pipes is way more expensive than to put the pipes on the surface, because you have to bury them deep. The high pressure has to be different material, and also you need divers, you need to weld under the water. It's just a lot of mess to install pipes under the water. To install pipe on the ground, hey, anyone comes in, like, put a few bolts together, you're done, right? So it's simple, much simpler. Just make sure it's level. So the cost of underwater pipes has to be much bigger than the cost of laying pipes on the ground. And clearly, we are presented with two options over here. One option is to run the pipes directly underwater, 100%, right? And we know that that calculation is going to be 2 squared plus 5 squared in terms of miles, right? It's the square root of 29. And for the square root of 29 is 5.4, about 5.39, so 5.4 miles underwater. Now, what is the cost? So we make up numbers. So if you know the power lines, right? And you know they stretch 5 wires in between. If you go and count, you will see 5 wires in between any 2 towers. So one tower with a set of wires that belong to that tower, right, is 100K. So this is 100K to install. And then you have the next tower with its set of 5 wires going the other way. And then you have the next one and the next one, right? So each one of these is 100K. So what about these pipes? Well, let's say that the cost for ground is, let's say, 200,000 per mile, and underwater, I'm just making this up, 500,000. This could be much cheaper than what actually is. I'm just toss any numbers out there. So, do we need calculus knowledge to calculate the black and the blue route and how much is it going to cost? Right, if this is the route 1 and this is the route 2. Well, the answer is of course no, right? We don't need calculus. To calculate route 1, we have the cost is going to be 2 miles underwater. So that's going to be 2 times 500,000 plus 5. I have no clue what just happened. 5 miles at 200,000 is going to give us 1,000,000 plus 1,000,000. For the 2,000,000, if we want to use the black route. Okay, let's see if we're going to do better underwater. So 2, the cost is going to be 5.4 miles at 500,000 each, because it's all underwater. So 500,000 each, and that's definitely going to be more, right? 5 times 5 is 25. So 270. If I calculated this right. So we're gonna verify real quick. So this is what we have for the cost. So clearly, even though this is almost mile and a half shorter to go directly there under the water, clearly the higher cost, it just right makes everything to be $700,000 more. We did not use calculus. Now we would like to optimize to find the optimal route so that the cost is minimum. And this is where you come in with your skills. You're sitting at a meeting, you're looking at these two calculations, and you're laughing because you know calc, and you say, well, we're gonna go actually on the ground for some time, and then we're gonna cut through water. And that's going to be your route 3, and you are proposing this because it's going to minimize the cost. They said, all right, how much do we save? Well, let's see. We're going to go X distance on the land and then D distance on the underwater. So when you combine two of those, the goal is to have the cost to be lower than the black or the green or the blue, right? Great. I know I'm minimizing the cost. Now, what is my constraint that it's connecting X and D from this geometry? Do you see it? The connection that will connect X and D. So where is the connection? It's tricky. It's the triangle. Do you see the triangle? That's the right triangle right there. So we can use Pythagorean theorem, right? But does this triangle have an X in it? I definitely have D in the triangle. How about X?
It's 5 minus X.
Yes. This side over here is 5 minus X. Because if the whole distance is 5 miles and the bottom is X, then that distance is 5 minus X. And I can have 2 squared plus 5 minus X squared equals D. That's a B. D squared. So there's my connection, and this is what we would call constraint equation, right? No min, no max, is just straight up. So D is equal to square root of 4 plus 25 minus 10x plus x squared. So D equals square root of x squared minus 10x plus 29. Now, cost equation, so this is my constraint. Cost equation is the one that I'm trying to minimize. So, I have X times 200,000, which are the pipes on the ground, plus D times 500,000 each for the underwater. And that's my objective equation. So now I plug in D. So we have 200,000 X plus 500,000 times the square root of x squared minus 10x plus 29 equals a minimum. And then you hit this with the derivative in x. So it's going to be 200,000 plus 500,000 times 2 times the original square root times the derivative of the square root on top equals a 0. $200,000 plus you can factor 2 and get x minus 5, right? And then the 2 will cancel. So we have 500,000, and then you have x minus 5 and the square root of x squared minus 10x plus 29. And all you need to do is to solve this. So x minus 5 over square root of x squared minus 10x plus 29 is equal to negative 2/5, because you ship 200,000 becomes negative, and you divide by 500,000, all the zeros cancel. So now you have 5x minus 25 is equal to negative 2 square root of x squared minus 10x plus 29. Actually, you know what? I'm just going to keep this way. So now when I square both sides to kill the root, we will also kill a negative. I have 25 times x minus 5 squared is equal to 4 times square root is gone, x squared minus 10x plus 29. So now this is 25 times x squared minus 10x plus 25 is equal to 4x squared minus 40x plus 4 times 29 is 4 times 31, 20 minus 4, 1, 16. So 25x squared minus 250x plus 25 times 25 is 625 is equal to 4x squared minus 40x plus 116. So that's 21x squared minus 210x plus, when I subtract, that's a 9 and a 0 and a 4. Is it 4 or 9? 5 minus 16 is 1. We stole 1. 1 minus 1 is 1. No, 5 or 9. 5 or 9. Then you go to Wolfram Alpha. And ask to solve this quadratic equation. Solve 21x squared minus 210x plus 509 equal 0. And then use approximate form to give you decimals. We get x equals 4.1 or 5.87, 5.9. Now, clearly, this is a bad number because x cannot be 5.9 if you have 5 miles, right? 5.9 is here. That makes sense? So we have to throw that solution away. And we just found that x is 4.1 miles. So what's d? Well, d you have to go and compute. You have the formula for d. It's the square root of this quadratic. So square root of 4.1 squared. No, there's a number in front. No, there is no number. 10 and 29. Okay. Minus 10 plus 29. Okay. So 4.1 squared minus 10 times 4.1 plus 29. So we have to compute this. So 4.1 squared minus 41 plus 29 is square root of 4.81. So square root of the answer is 2.2 miles. So what's the cost? The cost is 4.1 miles at 200,000 plus 2.2 miles at 500,000. So this is going to be 800,000, so 820,000 plus 1.1 mil to come up with 192000. You saved $80,000 like this with a 5-minute calculation. Would the company pay you $20K as a consultant? Sure, they still keep 60, right? So these are the calculations that come out of these types of problems. This is highly applied, right? And it's actually used. There are a whole bunch of other problems with other geometries, so you can try. I believe they have 6 or 7 pages of homework exercises in the textbook to practice. It's really good. So probably this would be the most important section in terms of your employment and life of Calculus 1, this 4.5 optimization. So that's how you make money. All right. We're going to take a break. When we come back, we talk about linear approximations and differentials.